Hello, everyone. Can you hear?
Yes, Joseph.
Okay, great. Business. I guess I'll wait a little bit for other people to show up. And I'm going to check to make sure that we're recording. Yes, we are. So done in the past, it hasn't started recording automatically. So sometimes we miss out on the recording, but this time it's going. So that's good. Okay, so while we're waiting to make sure that everyone shows up, are there any questions that any of you have at this point? Okay, are you seeing the screen that I'm sharing, which is the Notebook 3?
Yeah.
Okay, great. Just wanted to make sure. I'm actually running it now just to make sure I have all the outputs. But what I want to do is I want to go through this notebook and pay particular attention. I mean, this notebook is really for videos 4 and video 5. We've already done essentially video 4, and I've gone through parts of this notebook already. But today I want to focus on the part that has to do with naive Bayes and the language, the sentiment classifiers that we construct with naive Bayes. That's going to be the focus. But before that, I'll just sort of recap what we've been through already. I'll start scrolling through and stop me if you want to ask any questions on any parts of the notebook. So what we did first, we downloaded the IMDb data set. At first we just downloaded a sample of it, not the full data set, just to test our models to make sure that they're working. And that's something that Jeremy has talked about in the past, that it's often advantageous to work with a small subset of your data just to make sure until you get all your models built and make sure they're working. And then use the full data set. And the reason, of course, is that a lot of times the models take a long time to train, and you don't get feedback until the training is completed. And with a small subset, you can get the training, you can get this feedback quickly. That's the reason for working with the small piece of the data set first. So the first part is just to get that small data set and start looking at it. And we see that it has basically a training set and a validation set, and each one of these consists of just text strings, and reviews are stored in the form of text strings, and that's what the input looks like. So let's see, but FastAI has a really beautiful API to import the data like this, and it imports it into a series of hierarchical objects. It imports the data into label list object and a text list object and a category list object. The text list object holds the reviews, and the category list object holds the labels. And each of these objects has properties that you can explore by looking at them in more detail. And in this sort of rewritten notebook, I've done a little bit of that. I don't know if any of you have gone through it, but part of what I did was to explore these objects by looking at them systematically. So
just one quick question with regard to if you go up with respect to the 3 different label list, text list, and a category list.
Yes.
What's the purpose of making 3? Like, is this a text list and a category list is the part of a label list, or he has created separate label list? You can access the same information, and through a text list, you're literally accessing the same information again.
When I look at this, I see that they've built this to be as convenient as possible, and so it might be a little confusing at first, but once you familiarize with the structure, it makes a lot of sense. So I mean, at first, like you, I was wondering, what are all these different kinds of objects that I have to deal with here? But you can see here that there's a hierarchy, and the label list object has properties which are it has, okay, so the training set is stored in this label list object, and the label list object has properties .x and .y. X is the reviews and Y is the labels, and so then they define a special kind of object called text list for holding the reviews. So text list is a way to handle a list of reviews, and category list holds the labels. So category list is a special object that holds the labels. And you can find out about these objects by doing a DIR. Like if you have an object, you can do a DIR and see what all methods and properties are available. So to answer your question, there's a hierarchy of objects that they define, FastAI defined for convenience of manipulating the data. And the way it works is so smooth you won't even notice it. Like as you work through the notebook, you just see that everything gets done automatically, and it's all because of behind the scenes they've defined this hierarchy of objects that smoothly handles the data.
Yeah, okay.
Okay,
Is there any way I can see? So I'm assuming the text list is nothing but just a child of a label list. So it's when we are referring to a label list, let's say in a bracket 1, we are talking about like .x, which is nothing but a text list.
Yeah, that's exactly right. If you have a label list object, all label list objects have .x, have a property .x that you can see by just asking for, label list .x, and then you'll get that.
Okay, get it.
All right, so let's just keep going through here because I want to get down to, so there's a point here that I wanted to make. So there's a vocabulary object. The movie reviews object also contains a .vocab property. And the funny thing is, this is not shown. Usually you can see all the properties of an object by doing a DIR of the object. But if you do DIR of the movie reviews object, you won't see this .vocab property, even though it's there. So I'm not sure if this is an error in the FastAI library. It seems to me that it is. But anyway, when you look at this vocabulary object, you see that it's its own kind of object. What it is, it's a kind of reversible dictionary that translates back and forth between tokens and their integer representations. Remember that tokens are parts of words. There might be a whole word, it might be a part of a word, like isn't would be sometimes divided up into is and n''t. Those would be the two tokens that it gets divided into. Other tokens could be punctuation marks or numbers or like number representation. Like if you talk about the number 0 in a text string, then there's a token for that. So tokens are basically pieces, they're words and pieces of words and punctuation marks. But every token has a numerical representation too, because deep learning models need to work on numbers, not strings. So the vocab object is like a dictionary that translates back and forth between the tokens and their numerical representations. And it has two methods that we're interested in. The methods are stoi, which is string to integer, and itos, which stands for string to index. And I guess I said string to index and index to string, because the integers are actually indexes. So in this way, you can see that you can actually look at .stoi, which is actually what they call an object called a default dictionary, which maps, you can see it maps these tokens into their integer representations. And the other way around, the itos maps the indexes into strings. So it's just the itos is just a list, of strings whose positions in the list correspond to their numerical indexes, if that makes sense. Okay, so we talked, I think we moved through this a little bit. STOI is a default dictionary. And then I added something to the notebook to help you understand the default dictionaries. So you can go over this later. I'm just going to move through this a little quickly to get down. So the next thing we do is we map every movie review into a vector space, and the vector space is going to have a length or a size equal to the number of unique tokens in the vocabulary. And so if you look at all the movie reviews in a cumulative list of all the movie reviews, and then you look for all the unique tokens that you find, it turns out there are 6,016 unique tokens. So that means that we can map every review into a 6,016 dimensional vector. And how do we do that? Well, we have a list, we have a vector whose indexes correspond to the tokens. So, and then the entries in the vector correspond to the number of times that token appeared in the review. So this is a very low, it's kind of like a low dimensional, not low dimensional, but it represents the review in terms of what we call a bag of words. In other words, all we care about is all the possible words that are used in the review and how many times each word gets used. So if we represent the review that way, you can see that we're throwing away a lot of information, right? And what information are we throwing away? We're throwing away the sequential aspect of the review. In other words, which words occur in order, which word occurs before which other word, and so on. We're throwing away all of that sequence kind of information. We're just saying, it's like we're considering each word as a different colored marble, right? And we have a bag of marbles, and we characterize that bag of marbles by how many marbles are in the bag, and how many different kind of marbles are there, and how many occurrences of each different color are there. So how many red marbles, how many blue marbles, how many green marbles? That's the bag of words representation, where each word, or really what they mean is token, each token gets represented only in terms of whether it's used and how many times it's used. So does that make sense? The bag of words representation. It's kind of a very simple way of representing a movie review or any kind of a text document, right? And that's the sort of the view that we're working with here in the rest of this. So then the notebook goes on to show how you can make token counters and how you can get what we call the embedding vectors, which is the 6,016 dimensional vector that represents a review. Okay, so you can generate an embedding vector for every review, and then that's essentially the document term matrix. The document term matrix has the number of rows, has a row for each document, and each row is a vector, is an embedding vector that encodes that review in this 6,016 dimensional vector that's this bag of words representation. So does that make sense? The document term matrix, if there's M documents and N terms, and here term means token. So if there's 50,000 documents and 6,016 different kinds of tokens, then the document term matrix would be 50,000 by 6,016 matrix. Does that make sense to everybody?
Yes.
Yes. Okay.
Yeah, I would like to ask.
With regard to. Sorry,
Yes,
go ahead.
You go.
Okay, I'll go ahead with regard to the document term matrix. I understand conceptually. However, my question is, let's say when you represent this document term matrix, the column heading and row headings, where are they stored? In a sense, let's say if we are saying movie review, so rows, each row is each review. Which movie we are talking about? Is that the label for a review, and how we are storing it? Similarly on the column labels.
Okay, so that's a good question. So the column labels are from this string to integer dictionary. So the column labels are implicit. In other words, they're not spelled out anywhere. But what they are is, let's go back to where we looked at the vocabulary. We looked at the vocabulary, and here's the mapping from the tokens to the numerical representation, right? So in the document term matrix, the columns correspond to these indices. The first column, the 0th column corresponds to the token XX unknown. The fourth column index 4 corresponds to this. Column index 9 corresponds to the word the, right? So that is not spelled out anywhere except here. Okay, it's not in the matrix. There's no heading. It's not like an Excel table. It's just implicit that that's where the columns come from. They are the indexes that correspond to the tokens, right? And there are 6,016 different tokens, so there are 6,016 columns. Okay. Now, as for the rows, each row is corresponding to one movie review, and the movie reviews come in this list that you've imported from the data, right? This list called movie reviews. If you look at, I think we looked at movie reviews.train. This is just the first review. The movie reviews correspond to these texts. And as far as your question about which movie is being reviewed, I'm not sure that is in this data set. It must be somewhere, but I'm not sure where that is in this data set. I'm sure you could find out in the IMDb data set. There must be something somewhere where there's a list of which movies are being reviewed, or maybe they're not. Maybe there has to be. But your question about the rows is each row corresponds sequentially to one of the movie reviews that we've imported in our database, and the ordering is whatever the order is in the database. Okay, so that explains the document term matrix. And somebody else had a question.
Thanks.
Yeah, I wanted to ask how the amount of data to be stored in the vocabulary is selected. For example, there are 6,000 words in the vocabulary. So is it selected on the basis of how many times each word has been repeated, or is there a fixed number?
No, this is a very good question. So what's done is they take all the reviews in your database, and then they look at and then they just combine them together, combine all the strings together into one, and then they separate it out. Well, they separate out all the tokens for each review, right? And then they just combine them all into a big list, and then they convert that to a set, which asks how many unique elements are there, right? So, well, actually, before they do that, they say any token that is represented three times or less gets mapped to unknown. So if there are weird words that don't occur very often, those words are not in the dictionary. Does that make sense? If the word occurs less than 3 times in the entire database, then it doesn't get included in the dictionary. But all other words do. And from then on, it's just a matter of how many unique tokens are there. And that comes from all the reviews. So if you have another database that adds more reviews, then you would expect more unique token. Maybe some of the reviews would have words that aren't used in the previous reviews, and then there would be more tokens. So you'll see that when we consider the full IMDb database, the vocabulary is longer because it has lots more reviews, which end up having more words that weren't used in the sample, in the smaller sample, if that makes sense.
Yeah, it makes sense. I was just confused since the FastAI library's vocabs were somewhat rounded off. The IMDb sample database was around 6,000 vocabulary. The length of the vocabulary was around 6,000. So I thought maybe they used some kind of.
So that's the sample one has about 6,000 words in it. But the full database has more. I can't remember how many. We'll see later on when we deal with the full database. It has more tokens in it because it has more reviews, and those reviews use more words, more words that weren't used in the sample part. So if you had one review in your database, the way you would decide on the dictionary is you would just look at all of the tokens and see which ones were used more than 3 times, I think, and and then those tokens would be your vocabulary. So then if you had 2 reviews, you would have to combine all of the tokens in both reviews and then see which ones, and then see how many unique tokens you have, right? In any given review, if you just based your vocabulary on one review, you might end up with only a few hundred tokens because it only used a few hundred different words, right? But the more reviews you add together into your database, the more unique words you'll have, if that makes sense. Yes?
Yeah, thanks.
Okay. So there's the creating the document term matrix. And then the interesting thing about the document term matrix that we have to point out is that it's got a lot of zeros in it, right? Because not every review uses every word. So in fact, each review is usually about a few hundred words. So in a 6,000 dimensional space, only a few hundred of those dimensions are going to have numbers in them, are going to be filled. So the review has lots of zeros in it, and a matrix with lots of zeros in it is called a sparse matrix. It's interesting that we can examine the sparsity of the matrix with a special function in NumPy called SPI. Actually, it's in Matplotlib, I think. It's called SPI. And what SPI does is it plots a two-dimensional matrix where the marker, the colored points are just for the entries that have non-zero entries, and otherwise it's just white. So here's the document term matrix, and here it is plotted with SPI, and you can see its sparsity. That is, most of it is white space, and white space is for zeros. The interesting thing is the structure that comes out here. It's just very strange to me, and I don't understand this structure, why it should have these bands in it. So that's interesting. If anyone can explain that or figure out why that is, I would love to know. But anyway, this is a way of visualizing a matrix by a two-dimensional matrix. You can plot it with this function called SPI, and it will show you an immediate map of where the data is in that matrix and which parts are zeros. Yeah.
What does on the horizontal axis 1,000, 2,000, 3,000?
This is visualizing the document term matrix. So
okay.
These are the document numbers. The index along the y-axis going from 0 to 800 is the training set of reviews, because there are 800 reviews in our sample training set, right? So this is actually plotting the document term matrix. The index along the y-axis here is the document number, and the index along the x-axis is the term number, or the token number in our dictionary. So it has a length of 6,016. It goes from 0 to 6,015. Does that make sense? So each column is the terms. So for example, this column here refers to some term that has an index between, something like somewhere around 2,700 or 2,800 from eyeballing it. And it occurs fairly frequently, and if you trace down here, it occurs in a lot of different reviews. And then there's some terms here between here and here that don't get used at all in any reviews up until this number. So
that is very interesting.
It is an interesting structure, and I don't know. It might have something to do with the way they sort the reviews.
So after 4,000 to 5,000, my expectation would be like these things are like the stop words, where what you consider to be the stop words, the most commonly occurring words, which do not add much value, like D, A, and so that's what I would guess.
Those are actually towards the beginning, right? The most.
Why would you say? But it's the count, right? Count is, these are the values, the number of times they are occurring, right?
Actually, we're looking at whether they occur or at all. So we're not plotting the number of times.
Okay.
We're plotting
All right.
a blue dot if the word occurs and nothing if it doesn't occur.
Okay. Sorry.
Yeah. So the most frequent terms you can see they're down here towards 0. That's where the and all the very commonly used words are, and that's why there's so much density here, because every review has those words in it, But then here are the less common words as you go out towards as
So
you go on towards
okay,
the
they are rare documents. They are the rare terms.
Yes.
Then
Yes,
okay,
that's
right side is
correct.
okay.
Yeah,
Got it.
yeah. So next, we go through. Rachel goes through how sparse matrices get stored, and this is pretty interesting. This is some structure. These are some sparse matrices that you can look at their structure, and sometimes they have really interesting structure. The point being that most of it is empty space, right? And so it would be a waste of space and compute resources to store these things as regular matrices. And so they evolved this sparse matrix, these special kinds of sparse matrix storage formats. And the ones we're most interested in are CSR, compressed sparse row format. And then Rachel also mentions this COO, which is very simple to understand. It basically just says you're looking at all the non-zero entries, and COO gives you just the sort of the row and column of that non-zero entry. It gives you a list of non-zero entries and their row and column. So that's an easy representation, and its advantage is that it has an advantage that let's see, there's something in this table that shows you what its advantage is. Facilitates fast conversion. So this allows you to convert a matrix quickly. But CSR has compressed sparse row format, has other advantages, and that is fast operations. So a lot of times they're going to use compressed sparse row because when you do matrix multiplications and matrix additions and so on, that's fast. So that's one of the preferred formats. So compressed sparse row is interesting to us, and so we should define it. And they don't do that in the video or in the notebook, but so I decided to do it so that people would be clear on how it's defined. So what it has you can represent a matrix in compressed sparse row format by giving 3 lists. The first list is the list of all the non-zero elements. So we have a matrix A that has m rows, n columns, small m, and capital N number of non-zero values. Then you can represent it by these 3 lists. One is a list containing all the values, the non-zero values. Another is a list containing the column indices of all the non-zero values. And then the third list is the more complicated list. At least it's a little more difficult to understand. It's called row pointer. And it contains the index for every row. Row pointer has an entry. And that entry tells you the index in val of the first non-zero value in that row. So I don't know if we don't have any examples here. I think Rachel goes through some examples, but that's how you would put any matrix into compressed sparse row format. The interesting thing is what happens if there's no non-zero values in one of the rows. Well, then you still have to have an entry in row pointer of I, because row pointer contains an entry for every row. So the entry for a row that has no non-zero values in it, that row is all zeros, the row pointer for that row would just be none. And then by convention, you tack on an extra value on the end of row pointer that tells you the number of non-zero values that you have. That's kind of redundant information, because if you take the length of val or the length of call, that also tells you the number of non-zero values that you have. So then I ask, how many floats and ints does it take to store a matrix A in compressed sparse row format? And if you look at that, you just have to add up the number of values in each of these matrices, right? So this has n, capital N, floats in it, because we don't know what the values in array A are. We're just going to assume they're floats. This one has n integers in it because it's just indices, and then this one has m, that is the number of rows, plus 1, because the one you tacked on, it has m plus 1 integers in it. So the answer to this little question is it takes capital N floats and capital N plus m plus 1 ints to store the matrix in CSR format. And the point is that is a lot less than m times n. That's m times n is how many it would take m times n floats to store the matrix, to store the full matrix. If you ignore the sparsity and you just store every element in the matrix, right? All right, so then I go through and I mentioned, if you really understand, if you want to say you really understand the CSR format, you have to be able to do two things. You have to be able to translate any regular matrix A into CSR format, and we just gave a prescription for how to do that. And then the other way is to go from the other direction. If you've given us a CSR representation, you have to be able to go back and reconstruct the regular matrix from that. So I've written how to do that here. I've written some functions that do that for us. I won't go through all that, but according to our definition of what CSR matrix representation is, you can write a function to translate back and forth, and that's what I do here. I won't go through it here. And then here's what I was talking about. I go through some exercises to explore what's in the IMDb data, and here's where you can. And actually, Rachel has a couple of exercises here, which you can go through and see if you can, and try to get the answers. I won't do that here. But for example, I guess one of the questions is, how many times does the word "it" appear in the review? How would you do that? First you'd have to figure out, okay, so given a review, and she gives you this one review here, the review indexed by 1, and here it is. How many times does the word "it" appear in the review? Well, you can count it, and find out how many times it occurs in the review, but you can also do it by software, and that is you can use the vocabulary dictionary that is S2I to find out which index corresponds to the word "it," and then you could look in the you could convert this review into its embedding vector, and then you could look at the entry in the column for "it" and how many words and how many is in that, and so that's how you could do that. What else? I'll just go past these because okay. So I just wanted to review through video 4, and that's where video 4 ends, and video 5 material begins here, and so this is the main point of our meeting today, is to discuss the naive Bayes classifier. So I'll just read through this a little bit. The bag of words model considers a movie review as equivalent to a list of the counts of all the tokens that it contains. Remember the bag of marbles kind of thing that I was talking about? And each token corresponds to a different colored marble. So that's how you can think about this bag of words method. And I just want to point out that when you do this, you throw away a lot of rich information that comes from the sequential arrangement of the tokens into sentences and paragraphs. So it's interesting that this way of approaching movie reviews, we throw away a lot of information, and yet, as we'll see, we can actually do pretty well in gauging the sentiment of the review, whether it's a positive review or a negative review. And that's the goal. We're trying to build a classifier that actually just looks at all the words and decides, do we have a review that does this person like the movie or does this person hate the movie? And that's all we want, is a thumbs up or a thumbs down. That's what this sentiment classifier that we're going to build is. And the way we're going to build is we're going to use this naive Bayes method. So what is the naive Bayes? Well, first, before I say that, nevertheless, even if you're not allowed to read the review, if you're only given its representation in terms of a bag of words, you look at all the different colored marbles, you can still usually get a pretty good sense of whether the review was good or bad, and how you do it by just mentally gauging the overall positive or negative sentiment that the collection of words conveys. Yeah, so if you look at your bag of words and you find lots of instances of great and wonderful and marvelous and exciting and all that, that's a good sign, right? That's a good sign that the person enjoyed the movie and is going to give it a good rating. Or if you find words like boring or dull or bad or worse or stuff like that, then if there's a lot of prevalence of those kind of words, then you would think that the reviewer didn't like the movie. And so this is how, even without the information of the sentences and paragraphs, just the words and how many times each one was used, you could hope to get an idea of whether the review is good or bad. And that's what the naive Bayes classifier is trying to do. It's trying to encode that simple reasoning process that I point to over here, just looking at the, how many good words there are, how many bad words there are. The naive Bayes classifier is an algorithm that encodes this simple reasoning process mathematically. And it's based on two pieces of information that we can learn from the training set. One is the class priors, that is the probability that a randomly chosen review will be positive or negative. In other words, in our review set, if I have 800 reviews, how many of them are positive and how many of them are negative? So if I have 800 reviews and that's our training set for the sample, I haven't looked at how many are positive and negative yet, but suppose that 500 were positive and 300 were negative, then the priors would be 5/8 for the chance that a randomly chosen review would be positive would be 5/8, and the chance that a randomly chosen review would be negative would be 3/8, right? Does that make sense? It's basically the prior probabilities based on your training data that a randomly chosen review would be positive or negative. And remember that the training data, you have all the reviews and you also have the labels, whether they're positive or negative. So does that make sense, the class priors, that idea? Yes, no? Hello?
Yeah, fine.
Okay, I just want to make sure I don't lose my audience. All right, and then the other thing is the token likelihoods. That is, how likely is it that a given token would appear in a positive or negative review? So to get that, you would look, say there's a word that you're interested in, a token that you're interested in, let's say marvelous, right? The word marvelous. The token likelihood tells you for that token, for the word marvelous, says how likely is it that marvelous, that word appears in a positive review, and how likely is it that word appears in a negative review? And just as if I asked you that question, you would say that you expect that it's more likely to appear in a positive review than it is in a negative review, right? The word marvelous, right? Or the word great, You would expect that word to be more likely to appear in a positive word than in a negative review, more likely in a positive review than in a negative review. And the token likelihood just quantifies that. It actually says, of all the tokens that are in all the positive reviews, how many of them are, how likely is it that token is the word marvelous? Of all the tokens that appear in all the negative reviews, what's the probability that token is the word marvelous, right? That's the token likelihoods. Okay, and the important distinction here is it's not the probability that word appears in all the reviews. It's the probability that there's one likelihood for positive reviews and there's one likelihood for negative reviews, right? So they refer to the probabilities that token appears in all the positive reviews or all the negative reviews, respectively. Okay, and this is all the information that we need to build this naive Bayes model. So now we're going to go through how this all gets done. The first thing we have to do is focus on how to compute the necessary. So this is the boring part, is how to compute the information from the training data. So we need to compute the prior probabilities, these class priors, and we need to compute the token likelihoods. To get the likelihoods, we have to get the class occurrence counts. And so we're just going to go through computing these things. So this section is just going to, section 8 that is just going to be doing all the computations we need to get to our naive Bayes model. So I'm going to go through those, but I just want to show you that's where we're going. We're going to end up with all of the things that we need to build the naive Bayes classifier. And then the next section will actually build the classifier and run it, okay? So let's go through here, back to the beginning of section 8. And I'm just going to quantify all this stuff. Here's the priors, P for positive, P for positive reviews and Q for negative reviews. So the class priors is basically the n plus over n, where n is the total number of reviews that we have, and n plus is the total of positive reviews. So it's just a fraction of all the reviews that are positive. That's all P is. And Q, in a similar way, is the fraction of all reviews that are negative. Okay, And what I have here is n plus and n minus are the numbers of positive and negative reviews. N is the total number of reviews, so that n has to be the sum of the positive and negative reviews. And also, because a review has to be either positive or negative, I know that Q is 1 minus P. In other words, the fraction of negative reviews is 1 minus the fraction of positive reviews. All right, so that's the priors. That takes care of that piece of that piece that we need. The next thing we need is the class occurrence counts. And I've denoted these by, there will be an occurrence count for each token T, right? So I have CT plus and CT minus, which tells me for a given token how many times they appear in the positive reviews and how many times they appear in the negative reviews. That's what these class occurrence counts are. Okay, so every token will have a number here, CT plus, and it'll have a number CT minus. So it just tells you the number of times that token occurs in positive reviews and the number of times that token occurs in negative reviews. Does that make sense so far? All right. So next I do a little bit of data exploration here with the occurrence counts. Here's our movie reviews classes, and the classes, this is one of those clever structure things that they built into the FastAI library. MovieReviews.y gives you the classes, but then it also has a property. Sorry, MovieReviews.y gives you the labels, but it also has a property of classes, and it tells you that the labels are either positive or negative. Next we can just define integer representations. We're going to want positive reviews to be represented by 1 and negative reviews to be represented by 0.
There was another property called .c. Is it class dot classes? What's the difference between dot classes and a .c?
I'm not sure. Let's find out. Can we?
Same, I guess.
Yeah, it might be the same. So moviereviews.y.c, you're saying?
Yeah.
So that tells you the number.
Oh,
That tells you the number of different classes, the number of unique classes, I think.
Okay. Yeah. Okay.
Yeah. So yeah, it's fun to explore these things because they don't define these things. These structures that they've built in the FastAI library, they don't define them, but you can explore them by using dir. For example, if I want to understand what's in movie reviews, I can do this: dir movie reviews, and then it will show me all of these double underscore, these dunder things are all the sort of the hidden properties, and we don't need to be concerned about them. But there's all of these properties and methods that we have available because they've defined these classes in a way to make them as useful as possible. And a lot of these properties and methods we're not even using, but some of them we will use. For example, test. We're not using test because it has nothing in it right now, but train in this case has stuff in it, and valid has, train has the training set and valid has the validation set. Okay. Anyway, so that's how you can explore this on your own if you want to understand what's in this object called movie reviews. Anyway, so let's see, what do we want to do? We can define brief names for training and document matrix and its labels, the validations, the vocabularies. We just define X and Y, X to be the training data, the document term matrix that is, and Y to be the labels. And for the validation set, we define the labels to be this, to be valid underscore Y. And then vocabulary, we just define to be V, just for purposes of brevity here. Here are the counts. The count arrays list the total occurrence counts of the tokens, of each token in positive and negative reviews. So this is that C plus and C minus that I talked about. C plus is the C1, 1 corresponds to positive reviews, and C0 corresponds to the negative reviews. And then this will be a vector which will have 1 entry for each token in it, right? So for each token, we sum up how many positive reviews it is in and how many negative reviews it is in. And there are that's what these are. So you see what I did. I took the array of X, that is the array of tokens, and then I looked for the positive reviews, and then I summed up over all the. I asked for each token that occurs in a positive review. and then summed it all up. So for each token, I'm summing up how many positive reviews it's in and how many negative reviews it's in. And so if you look at this vector, C1, it has all of these occurrence counts in it. So I'm looking at the first 10 entries. And so, yeah.
What is the purpose of this squeeze?
Squeeze. What squeeze does is it collapses one dimension. So if you look at X, let's see, X dot shape. If you look at the shape of X, it's 800 by 26. Let's see, X 260402. Why are there? Trying to figure out why. Train dot term. I'm a little confused here. Let me see something. Oops. Why? I have to execute it. Let's see.
So the X is the train.
Oh, it doesn't have.
It's a term document.
Pardon?
So the X is it's not a training set, but it's the document term matrix. That's
document
why.
Term, yeah, document term matrix.
Yeah.
Now, a little confused because the way I thought I set this up was that the document term matrix has 6,000 entries in it. Let me see. Let me see where I put train doc term. Edit. Okay, train doc term. Train doc term equals R. Oh, I know why this is wrong, because I ran this whole, I ran the whole notebook before I started, and so at the end it was dealing with the whole, the entire move reviews database. So it's not, let me see. So that it's not where we are in the notebook now is we were looking at the sample set. So if I wanted to, I don't want to run the notebook all over again. I should run the notebook from the beginning just to get to where we are now. So because before we started the class, I ran the notebook all the way through to completion, where at the end of the notebook, it was dealing with the entire database. And that's why the numbers are a little, that's why when I look at the numbers in that document term matrix, it doesn't look right. And that's because it's the document term matrix for the entire database. So, but I did look along the way, if I don't execute anything, if I just look at the things that were already executed, then we can see what was really happening. So let me go back here to where we were. We were looking at the counts. So this is the count vectors, and I'm looking at the first 10 of them, and it just gives me the counts, how many times this token was used in all the positive reviews, and how many times this token was used in all the negative reviews. So if I add these two up, that tells me how many times the tokens was used in all of the reviews. Does that make sense? So this particular token was more likely to be used in negative reviews than it was in positive reviews, and so on. Okay, and this token was more likely to be used in the negative reviews because remember, the second list is the 0 is the counts corresponding to negative reviews, and the first list is the counts corresponding to positive reviews. So here, there are things you can do now with these C0 and C1 once you've built them, which we have over here. You can ask how many times does the word love appeared in negative and positive reviews. And I made a mistake here. That's what it should be. So I look up the index for the word love, and then I just ask for how many times does the word love appear in positive reviews, and then I get the answer here. And I do the same thing for negative reviews, and then I find out that respectively in all the reviews, love appears 133 times in positive documents and 75 times in negative documents. which makes sense, right? If the review is negative, you don't expect to see the word love in it that much, right? But if it's positive, you do. Okay, how many times does the word hate, again, hate, appear in negative and positive reviews? And it turns out that hate appears 5 times in positive reviews and 13 times in negative reviews. And again, that's what you'd expect. Hate would be more likely to appear in negative reviews, right? And then Rachel had some ideas. Let's look for an example of a positive review containing the word hated. And she actually found one. And a negative review containing the word loved, and she found one. Or she found actually several. So she's just looking at one of them. Okay, that's just interesting. Okay, so next we come to computing the class likelihood ratios. So the likelihood ratio is the number of times that the token appears in a positive review divided by the number of positive reviews. So that's the likelihood. That is, given that it's a positive review, what's the probability that the word will occur? And that's what this likelihood ratio is. And I've made some notation for it, L of t given plus. The bar here, you'll often see this in machine learning and mathematics and so on. The bar means conditioned on. So L of t bar plus means the likelihood of this term occurring given that the review was positive. Conditioned that, given that, conditioned on that the review is positive. Does that make sense? That this notation, this bar notation, means the likelihood of the term t given that the review is positive. And again, the likelihood of the term t given that the review is negative. And so I've defined I've defined these likelihoods that way.
So do you read this likelihood of term in, like, when you say likelihood of a term t given positive review, likelihood in which review, positive or a negative?
Likelihood, when I have the first one says likelihood of t given that the review is positive. So this bar means given that, and then plus means the review is positive. So L of t bar plus means the likelihood of this term t occurring in a review given that the review is positive, is known to be positive.
Okay.
Okay. And so so based on the terms that we've defined so far, that's calculated this way. It's the total number of times that the term has occurred in positive reviews divided by the number of positive reviews. And the same way for negative reviews. Okay. And then there's this useful ratio that we can define called the log likelihood, the log count ratio, R. It's the log of the ratio of these two things. And R just tells us, it basically gives us a measure of this term, whether it's more likely to occur in positive reviews or negative reviews. So if R is greater than 0, remember logarithms can be either greater than 0 or less than 0, or 0 actually. So if RT is 0, we can start with that. That means that the likelihoods of being in a positive review or a negative review are the same. So a term that has R equals 0 is kind of a neutral term. It's equally likely to appear in positive or negative reviews. If LT is greater than if the numerator is greater than the denominator, then the logarithm is going to be greater than 0. And so that means that positive reviews are more likely to contain this token. This token is more likely to be associated with positive reviews. So a word like love or good or exciting would probably have an R greater than 0 because it's more likely to occur in positive reviews. And same way, if LT minus, if that's greater, then this log is going to be the logarithm of a number that is less than 1, and then that logarithm is going to be negative, right? And so any term that has an R less than 0 means that negative reviews are more likely to contain this token. So this R is kind of a nice measure of the sentiment contained in a word, whether it's a positive sentiment or a negative sentiment. And it's going to be useful for us, as we'll see later on. Okay, so the next step is actually build the naive Bayes classifier. And so the, let's see, where are we here? The likelihoods as I define them here are, there's actually a little trick that when they actually compute the likelihoods, they actually add 1 to the numerator and the denominator just to make sure that that they don't get that things are numerically stable. So here's how you define the likelihoods with that extra trick, the extra 1 added to the numerator and denominator. And then here's how you compute the log count ratios. You just take the ratios of these two things as we did here. R is the log count ratios. So here I'm just implementing it in code. Okay, R is NP log of L1 over L0. And you can see what they look like. There's some of them are 0, some of them are positive, some of them are negative, as we would expect. And then we could go through a little exercise here, get the indices of the tokens with the highest and lowest count ratios. We can ask for those indices, and then we can ask for what words they are. So here are the words that have the most likelihood of appearing in positive reviews. Some of them are incomprehensible to me. I guess, well, Jabba means Jabba is the Jabba the Hutt that appears in Star Wars. So that, I guess that's that. Astaire, noir. People like noir movies. People like Fred Astaire movies. People like sport movies. I'm not sure why Biko stood out. That's weird. What movies? Okay, then we just go through a little exercise of looking into which movies have Biko in them and so on. It's just a little exercise in curiosity. And here the most negative words are crater, Soderbergh, crap, porn. So some of that makes sense. Worst, yeah. So that's just trying to see if these log count ratios make any sense. Okay. Okay, so now we go to the actual computation. We're continuing to do the actual computation steps for the naive Bayes model. Here's the prior probabilities. This is, we define them up above in formulas. This is how you actually compute them in code. Remember, P is the number of fraction of reviews that are positive, and that's how you get this is how you get that fraction. Q is the fraction of reviews that are negative, and so on. And here we found for our data set, for our sample data set, roughly 48% of them of the reviews are positive, and 52% are negative, we find out. And then we can compute this ratio because it's going to figure in our model the logarithm of the ratio of P to Q. That measures the bias or imbalance in the data set. If B equals 0, that means that P and Q are the same, right? If P is the same as Q, then we're talking about the log of 1, which is 0. Then B would be 0. I call it B because B stands for bias, so that's just a convenient name. If the reviews were equally balanced, if there were as many positive reviews as negative reviews, then B would be 0. If B is smaller than 0, that indicates there's a bias towards, oh, it's the log. P is, B is greater than 0, then there's a bias towards positive reviews. If B is less than 0, indicates a bias towards negative reviews. That's just from this definition, right? If Q is greater than P, then P over Q is going to be less than 1. And then the logarithm of a number that's less than 1 is going to be negative. And so B would be less than 0. So B indicates the bias in our data set. And if we actually go to compute it for our data set, it's going to be minus 0.08. So it's slightly biased towards negative reviews. Okay, and now here's the main part of the explanation of the naive Bayes classifier. What we would like to do, we would like to predict the probability that the review is positive or negative given the tokens that it contains. So this is what we aim for, this P of class given the tokens. And remember, tokens is the bag of words, is basically the set of all the words that the review contains. So given that, I want to be able to predict whether the review is, what's the probability that the review is positive or negative. That's what I want to get. Okay, that's what I'm after. And how can we do that? Well, Bayes' theorem gives us a way to do that. Bayes' theorem tells us that the probability of the class given the tokens is proportional to the probability of the tokens given the class times the probability of the class. I don't know how many of you have seen Bayes' theorem or not. If you haven't seen it, it might be good to look at this Wikipedia article. But let me, for those who haven't seen it, I want to just do something here to sort of make it believable to you. Suppose you have two things, A and B, two events A and B, and you can ask for the probability that A and B both occur. Well, you can write that as the probability that A occurs. Sorry, that's not what I want to do. You can write that as the probability that A occurs given that B occurs times the probability that B occurs. Does that make sense? In other words, if you know the probability of A conditioned on B and you know the probability of B, then multiplying them together gives you the probability that both of them occur. Similarly, you can write the probability of A and B in another way. As the probability that, am I using capital P's for probability? Yeah, I guess I'll stick to that. Similarly, you can write the probability of A and B occurring is the probability that B occurs given that A occurs. So that's the conditional probability of B times the probability that A occurs. They both give you the same thing. So you can equate those two things. You can equate the right-hand sides and write the following statement. And this is nothing less than Bayes' theorem. It's a statement about conditional probabilities. And so all we're doing in the naive Bayes classifier is we're identifying A with the class and B with the bag of tokens and applying this thing, right? So I can write, I can rewrite this whole thing if I want now. Now I'm going to apply it. Okay, A is going to be identified with the class, and B is going to be identified with the bag of words. Which is basically all the text in the review. Right? And so you can rewrite this statement. Okay, let me, okay, so that's the statement of Bayes' theorem. Now I want to apply it to our movie review problem, so I'm just going to make the substitution here, straight substitution. Just as I said, everywhere I see an A, I'm going to put class. And everywhere I see B, I'm going to put tokens. Okay, and so you can see that what I'm after is to compute P of class given tokens. So let me get that by itself on the left-hand side. I'll just divide through by P of tokens here. And so what I can write is that P of class given tokens is equal to this stuff divided by P of tokens. Now, in this statement here, this is what we want. This is the probability that the review will be positive or negative given the tokens. This is the token likelihoods, the probability of the tokens given the class, which we've already computed. This is P of class, which we've already computed. And then this is just a constant, which we haven't computed, but we don't care about. And how we're going to find out we don't need to care about this thing. And the reason is, well, I can write this as, for now, our statement would be P of class given tokens is proportional to and that's the statement that we're starting. That's the naive Bayes classifier right there. The probability of the class given the tokens is proportional to the probability of the tokens given the class times the probability of the class. And remember, these are the class priors, and these are the token likelihoods that we know how to compute these things. So at this point, we can say we're done. We know how to compute this stuff. But the interesting part is actually putting it all together and writing it down and applying it. So let's go ahead and do that. There's a few more steps. Let's see. So this is where I just what I just showed you. Actually showed you all the steps to get this, right? This is our starting point. So if you didn't know Bayes' theorem, go to the, when you have a chance, go to the Wikipedia article, look it up. It's really important for all of machine learning. But I gave you a little taste of it. I actually derived Bayes' theorem right here. And it's really simple. It's really simple. So this is it, right? This statement here is Bayes' theorem, and that's all there is to it. So we then went and applied Bayes' theorem to we saw how Bayes' theorem can be applied to our problem to get this statement. And then that's where I start here. I just write it in, I've typesetted this in LaTeX. All right, now I'm just, I'm going to mention that the tokens are not independent of each other. For example, go often appears with to, like go to hell or go to the store or whatever. If go appears in a review, it's more likely that the review also contains the word to. So the tokens are not independent of each other. Nevertheless, if we make the assumption that the tokens are independent of each other, even though we know it's wrong, it might not be that wrong. And so we might get something good, and that's what we're going to do. That's what the naive Bayes, that's what naive means. Naive means you just go blindly ahead, even though the tokens aren't independent of each other. We make the assumption that they are and see where it leads. So we're going to recklessly move ahead and hope that we're not too wrong when we make that assumption. So if we make that assumption, then we can write the likelihoods, the token likelihoods, as the product of all of the all the likelihoods for all the tokens. The probability that a given set of tokens will be associated with a given class would be the product that each token gets associated with that class. So it's the product of all the token likelihoods. So here, Ti is the ith token of the vocabulary, and N is the total number of tokens of the vocabulary. So now we can write Bayes' theorem a little differently. Probability of class given tokens, we can replace this piece here with this. So I've just taken this term, replaced it with this product, and there it is right there. Probability of a class given the tokens is proportional to, so this is the part where we get to, so remember we completely ignored the term probability of tokens, and this is why. Remember back up here. Remember I have this term here. If I wanted to fully account for it, I would have to figure out what P of tokens is, but I don't, and I'll show you why. So I ended up saying, I don't care what P tokens is, it's just a constant. And all I need to know is that probability of class given tokens is proportional to the rest of it, right? And now you'll see why I don't need, why the proportionality is all I need. Because I can write this for the positive class, I can write this statement, and then I can write an equivalent proportionality for the negative class, and then I can take the ratio, and then the proportionality constant divides out. So that's what I've done here. Replace P, so I have a statement, P plus given tokens is proportional to P plus given P times the product of the token likelihoods for the positive class, and then I have the same statement for the negative class, and then I just take the ratio of those two statements, and then I get this equation here. Does this, I haven't heard from anybody. Does anybody have questions up to what I've done here? If there's anything, doubts or something I did that didn't seem obvious or whatever, please ask and I'll try to address your question. If you have a question, probably other people have the same question, so don't be hesitant to ask. No questions up to here? Have I lost audio?
No.
You're there? You're still there? Okay.
We are here.
Okay, great. Okay, so here's this, so starting from this ratio, then we take the log of both sides to convert everything to, instead of a product, we convert it into a linear problem where everything is in terms of sums. So I take the ratio of this equation. You can see what I have is log P over Q, which is our term B, our bias term, plus, and now we're going to convert this product to a sum when we do the logarithms, right? Because the log of a product is the sum of the logs. And so now you can see why we define this R, this log count ratio, because it occurs, it's so convenient, it occurs in this equation. It's the log of the ratio of the token likelihoods for the positive and negative classes. So now we have this log likelihood, this log ratio, in terms of all the things that we've already calculated. We've calculated B above in the notebook, and we've calculated these log count ratios R. Now let's say a little bit about the left-hand side here. So the left-hand side is, we already talked about it a little bit. The left-hand side is greater than, if the left-hand side is greater than 0, we predict that the review is positive. And if the left-hand side is less than 0, we predict that the review is negative. That's the mathematical formulation of the simple algorithm we talked about by looking at the bag of words and seeing whether it contains mostly positive words or negative words. That's what a human being would do if they were asked, if somebody told you, I'm just going to give you the bag of words representation of this review, and I want you to determine for me if it's a positive or negative review, your brain, your mind would say, okay, let's look at these marbles. Let's look at how many positive words there are and how many negative words there are, and I can get a feeling for whether the review is positive or negative just based on the occurrences of positive and negative words. Even if somebody didn't give me the text of the review so that I could see all the sentences and paragraphs laid out, right? So this naive Bayes is basically a mathematical implementation of that simple thought process. All right, and so I'm going to write this as, okay, I make a point here that, an interesting point here, that is that the second term here is the dot product of the binarized embedding vector and the log count ratios, it turns out. So when Rachel talks about the binarized naive Bayes and the naive Bayes, I find that when I derive naive Bayes, it comes up naturally in the binarized form. And so it's not surprising to me that the binarized form gets a better result, as we'll see later on. It just falls out naturally in the way that you define, in the way that naive Bayes is stated. It just turns out that it's already using the binarized embedding vector. That's a subtle point, but that's what I found out when I derived it. So here's the statement. Yes.
So what would be the binarized embedding vector?
Oh, okay, fine. I'm sure. I'm glad you asked that question. So remember, the embedding vector is a vector that has an entry for each token in your vocabulary, and that entry tells you the number of times the word gets used, right? So, you know, if the word the got used 9 times in this review, then that word the entry for the, which is the 9th, let me say it again. If the word the gets used 20 times in a review, then remember the word the is the 9th entry in our embedding vector, because that's what the vocabulary said, right? When you look up string to index of the, you get 9, I think. And so the 9th entry in that embedding vector would be the number of times that the got used in that review. So the binarized embedding vector converts, it says, if that entry is greater than 0, just make it 1. In other words, just an indicator to say that the word the is used in the interview. I don't care how many times it was used. Just if it was used, I get a 1 there. And if it wasn't used, I get a 0 there.
So in a sense,
the binarized embedding vector just converts all of the counts into 1 or 0.
Okay, so we are saying in general, we were looking at but I don't think in the past we look at any weightage was given anywhere to the number of times any word was appearing.
That's right. And that's the counts. The only weight that you have for the words is the counts. So what is true here is that this thing here is basically the dot product of the log count ratios with the binarized embedding vector. And that's what I've got here, where W is the binarized embedding vector and R is the log count ratios. If you take W dot R, you will get the sum of all the R terms for a given review.
Okay.
Does that make sense?
Yeah.
So if you just, this W actually is for the 2-dimensional, all of the reviews, but if you just took one row in W as the row corresponding to the first review, let's say, then W, what's in W? W, I said, is the log count ratios. So it's that review converted to, I'm sorry, back up again. W is the binarized embedding vector, I said, for that review. So that means take the counts, you know, that line in the doc term matrix, which tells you the number of counts for each word, and convert it to a binarized vector, which means if the counts are bigger than or equal to 1, replace that count with just 1, and if they're 0, just leave it at 0. So the binarized embedding vector has only entries of 0 and 1. 1 if the word was used at all in the review, and 0 if the word was never used in the review. And if you take the dot product of that with the and what is the length of W? The length of this binarized embedding vector is 6016. It's the number of terms in your vocabulary. And the dot product of a vector with another vector, R is a vector, is a column vector corresponding to the log count ratios for each term. And since there are 6016 terms, capital R has 6016 entries. And if you take W dot R, you will get, that is the first line in W dot R, you will get this summation, the sum from I equals 1 to n of RTI, where you're summing over all the terms. It's basically a dot product of a row in the document term matrix with the column vector that is the R, the log count ratios. So that's a way of writing this equation, this one here, in a simpler form in terms of a matrix. And I've defined what I mean here. W is the m by n binarized term document matrix. You just take the term document matrix and convert all the numbers to that are greater than 1 to 1, and leave the zeros as they are. Okay. And R is the n by 1 column vector of log count ratios for all the tokens. So it has a length of 6016. And B is an n by 1 vector. I have to define B, capital B, as a vector, but it's just a vector, an n by 1 vector whose entries are all equal to the same number, which is the bias B, which we've already computed. So what is our naive Bayes model? The naive Bayes model consists of the log counts vector and the bias. Those are the two pieces. Once you've computed those two pieces, and the document term matrix for your for your database, then that's all you need to make the predictions. Okay, so now all we have to do is do that. Let's just let's do that. We can do this, apply this to the training set, and we get prediction accuracy of 90%. That's not a surprise because that's the training set. We know all the answers. But the more interesting thing is when we apply it, we apply our naive Bayes model to the validation set. Now we don't expect the accuracy to be so high because the training set, the naive Bayes model was built on that data. Now we're applying the naive Bayes model to documents that weren't seen, that it doesn't know about, that it hasn't seen before. And now the accuracy is much lower, but it's still pretty good. I mean, almost 70%. Okay, and in Rachel's spreadsheet, she makes two different applications of naive Bayes with a binarized and a non-binarized form, and the naive Bayes in the non-binarized form, I think, gets an I didn't do that, but it gets an accuracy of 64%, so it's somewhat worse. And to me, the reason is that when you derive naive Bayes, it naturally comes up in the binarized form. So what I should mention here is that this is actually the prediction for binarized naive Bayes. Okay, then I have a section here that sort of summarizes for you, because in your work as data scientists, you're going to you might end up being asked to compute a naive Bayes classifier and use it. So here's how you would do that. I'm just going through the process that we already went through earlier in the notebook. First, you compute the token count vectors, then you compute the class likelihood vectors, then you compute the log count ratios, then you compute the bias term, and again, the naive Bayes model consists of the log counts vector R and the bias B. That's all you need. And then the other piece of it that you need is your data, which is in the form of W, the binarized term document matrix. So this gives you the complete prescription for how you can go about computing a naive Bayes classifier from scratch. And the interesting thing about naive Bayes is there's no calculus, there's no stochastic gradient descent. It's just an analytic formula. And that's one of its advantages, is that it's very quick to compute. It's fast, and it doesn't require a lot of compute resources. Okay, so the next thing you do is now we've tried out our model on a small data set. The next thing to do is to move to a larger data set and do it. I'm just going to move through this really quickly. Create the document term matrix, save it. And I have a section here of a little bit more of understanding what all of these objects that you find in FastAI's API for text data sets, because they've built this really nice API. So I'm going to go, I go through it. I'm not going to do it now, but you can go through it at your leisure. We're just examining all of these objects in a little more detail that you get from their, from FastAI's application programming interface. I'm just going to go through this really quick. I described textless objects. There's text objects. They've defined all of these objects in their application programming interface and defined all the properties that they have. Category list, we've talked about this a little bit. Category is another object. So it's just exploring what you have in this interface. Gets you familiar with some of these objects. Okay, so the next thing we do is we apply the naive Bayes classifier to the full data set. We construct it the same way that we did before, except now with the full data set. Everything's the same. We run it. Bias term in the full data set was designed to have the same number of positive and negative reviews. So by design, the bias it's an unbiased data set. The bias is 0. So the bias term is 0, and the bias vector is just a column vector of n zeros. It doesn't even figure into the model. We do the same thing. We make a prediction, and we get 83% for our full data set. So that's a huge improvement. It means that having more data got us a lot. It got us, instead of 800 reviews, I think there were, I can't remember, 50,000 or something. I don't remember. Anyway, we got a huge improvement by getting more data. The next thing that that Rachel does is says, okay, there's another way to compute this. We can just use logistic regression, and you can use either the binarized document term matrix or the regular document term matrix. And again, the binarized got you a slightly better result. So now we got 88.5% using logistic regression. So after all that work to develop the naive Bayes classifier, we find that actually it's not the best. We find that logistic regression does a better job. The next thing that that Rachel does is she explores the Trigram model, and what that is instead of representing the review as a bag of tokens, you can represent the review as a bag of n-grams, where n-grams are sets of consecutive words. So a single token would be called a unigram, a 1 gram. A set of 2 tokens that occur together, like I'm going, or like
Not too good.
actually I'm going is actually three tokens, because I think it's represented as I and apostrophe M. So what was the comment?
Not good.
Sorry?
Not good.
Yeah, that could be a bigram, a set of 2 words that occur together. That's cool. Yeah, that could be a set of 2 words that occur together, and a trigram is a set of 3 words that occur together, like that's very sad or something like that. That's a 3 gram. So in the trigram model, it's a little confusing because trigram means 3 words, but what it means is a set of all the unigrams, bigrams, and trigrams. And so you represent the review as a bag of n-grams up to n equals 3. It's a simple, I mean, it's a similar way of representing the review. And so the modeling gets done in a very similar way. Instead of a document term matrix, we have a document n-gram matrix. And to do this, because there's a lot of different, once you open the door to having n-grams, you get a lot more terms, a lot more columns in your matrix. And so Rachel only did this with the sample. She went back to the sample data set instead of the full data set for this part. So we go back to getting the sample data set. Rachel wrote I found this problem. I don't know if anybody's tried to run this, but I got on my Windows machine, I kept getting broken process pool errors whenever I try to use this wonderful API that FastAI wrote. I got a problem that sometimes I get this broken process pool error. But being a really persistent guy, I kept trying it again and again, and I found out that sometimes it works and sometimes it doesn't work. So it's a really weird kind of an error. There's something wrong with the library that they haven't fixed yet, and maybe it's hard to fix. But so to get around this, I wrote this little thing that just basically does by brute force. It just keeps trying until I succeed. And sometimes it succeeds on the first try. Sometimes it takes a lot of tries to succeed. But it eventually does. And so that's how I got around this broken process pool error, if anybody encountered it. Okay, so the next thing to do is to create the n-gram doc. Instead of the term doc matrix, we need an n-gram doc matrix to encode the n-gram features instead of just the token features. So there's a little routine that Rachel wrote to do that. I won't go through all the details, but you end up with this n-gram doc matrix, just like we had a term doc matrix before. Looking at some of the n-grams, never mind, that's one. Have, an, are, within. These are sets of words that occur together, that are commonly occur together. Some of them you can't really decipher because this is unknown, involving unknown. That's not nothing we can figure out, but you can see what an n-gram means. Are within, that's a bigram. Are within is a combination of 2 words that occurs, that sometimes occurs within the reviews. Okay, so create the n-gram doc matrix. That's this. Save it so we won't have to compute it again. Load it. Now we build a naive Bayes classifier using trigrams instead of tokens. The math is all the same, except instead of the binarized term document matrix, we have the binarized n-gram document matrix. So so here's naive. I'm just going to go through the results because we've already seen the formulas and everything. What we end up with is see, an accuracy for the full trigrams model is 0.76. And then if we do binarized naive Bayes, we get 0.73. Wait, what's this full? Let me understand what binarized naive Bayes with trigrams. Blah, blah, blah. Binarized naive Bayes is 0.735. Then what was the other one that I just saw that said 8.3? Go back. 15A is naive Bayes with trigrams. Predictions, accuracy of naive Bayes with full trigrams model, 0.76. Okay, so here, this is the reverse of what I said before. I get better accuracy when I don't use the binarized, when I use the full trigram document matrix rather than the binarized version. I get a slightly better accuracy. That's a little puzzling to me, but that's what happened. We got 76% when we don't binarize the term document matrix, the n-gram document matrix, and we get an accuracy of 73% when we do. I think I have run over. I'm supposed to go till 9:30. I'll just quickly run through the end. Then we can run logistic regression again. And in fact, I'm just going to cut to the chase. I have a table at the bottom that shows all the results. Oops, what happened? I have this thing. It worked before. Anyway, I wrote a table that displays all of the results. Anyway, we can just look at the text that I wanted to print. I'm not sure why this didn't run this time, but here's the results of all of the modeling that we've done in this whole notebook. So we already saw the 64.5. That's from the video. I didn't do it. The binarized unigram model, that's the first thing we did with the naive Bayes. I got 68%. We just saw the naive Bayes with the full trigram model got 76%, with the binarized trigram 73.5. Then we went to logistic regression. Full trigram, we got 78%, but when we used our trigram, that is the one that Rachel computed, we got 80%. So we got two results. One was from the I guess scikit-learn trigrams, and one was from Rachel's trigrams, and she got a better result. Binarized trigrams, we got even a better result. And then it turns out that when we used the log count ratios, we got even a better result. That is with logistic regression, I'm sorry. That's these three. And then going back to the full database, we saw this with naive Bayes, we got 83.3%. With logistic regression, we got 83.3, sorry. With logistic regression, we got much better, 88.3. With logistic regression, with binarized trigrams, we got a slightly better result. So that's all the models that we ran in this spreadsheet. And I have to figure out why this last cell didn't run. Everything else ran, but the last cell didn't. I wanted to make a nice table to show all the results. And that's it. That's it for this thing. Next time we'll look at video, I think video 6, and we'll probably review this a bit, and then we'll look at the regular expressions, because that comes up in the next video. So any questions or doubts or comments? If not, thank you for being here, and I'll see you next week.
Thanks, Joseph.
You're welcome.
Okay, thanks, mate.
Okay.